So in this part of the lecture, we will show you how to compute the solution for the L2 norm regularized least squares. So let's see the objective function. So the objective function is norm of y minus 5 times w square plus lambda times norm of w square, where this lambda is a hyperparameter and lambda is greater than 0. If lambda is equal to 0, then what we'll get is just least square. So lambda is greater than 0. So the w is given by argmin over w. So let's minimize this objective function, right? So later in the course, we will learn that this is a convex optimization problem. This entire function is convex in W, right? And that's why once we minimize a convex function always has a global minimum. So by computing its gradient and setting the gradient to 0, we can get a global solution for the parameters W. We are using the convexity of the function over here to derive this result. So let's set the gradient to 0. Let's compute the gradient of this function. So let's call this, so the gradient of the objective function or the loss function with respect to W is the gradient with respect to W of y minus 5w transpose y minus 5w plus gradient w of lambda times w transpose w. So here we just use the definition of the norm, which is w transpose w, and the definition of L2 norm squared basically. So this is gradient with respect to w y transpose y minus y transpose times 5w minus w transpose 5 transpose y plus w transpose 5 transpose times 5 times w plus lambda times w transpose w. So this is a scalar. So listen, this is variable a and this is variable b. So we know that a transpose b is same as b transpose a. So this is same as this. These two terms are exactly the same. So what we get is gradient with respect to w lambda times I, where I is an identity matrix, plus 5 transpose 5 w transpose w. So we just use, we can just replace, we can just plug in an identity matrix over here, right? So w transpose times I times w is just w transpose w. So this is what we have done. We just replaced this by lambda I. So we took lambda I common and 5 transpose times 5 common. This is w transpose lambda I plus 5 transpose times 5 times w minus twice of y transpose 5 times w plus y transpose times y. And when we take the gradient, we set it to 0 to obtain the solution, the value of w that minimizes the loss function. So this is twice of lambda I plus. So if you remember our first lecture in least squares, we did this derivation. We computed the gradient 5 transpose times 5 times w minus twice of 5 transpose times y and the gradient of this with respect to W is 0. So which means that W is equal to lambda times the I is an identity matrix, plus phi transpose phi inverse times phi transpose times y. So this represents the solution for the L2 norm regularized least squares, right? And this has many advantages. For example, the phi transpose phi, this matrix might not be invertible, right? For example, its determinant might be 0, right? So in that case, if we have sufficiently large lambda such that lambda is greater than or equal to if we select lambda such that lambda is greater than the minimum eigenvalue minimum eigenvalue of the matrix phi transpose phi, then the resulting matrix is positive definite, and then the entire this thing is invertible, right? So basically, like with the higher the value of lambda, the smaller the values of W would be. So if we select lambda as infinity, right, then this inversion would be the 1 over lambda, in denominator we have like something like lambda, so that would be infinity, and this entire multiplication would become 0 because we have an inverse over here. Likewise, if lambda is equal to 0, then what we get is L2 norm, the regular least squares without the L2 norm regularization, right? So if lambda equal to 0, when lambda is equal to 0, then we obtain the solution as W equal to phi transpose phi inverse times phi transpose times y, which is a regular solution of your least squares problem. And with lambda not equal to 0, this is a closed form solution. So obviously again, like this would require us inverting an n by n matrix. This matrix would still be n by n, and inverting this matrix for very large, when it is very large, may be very complicated procedure. And again, like we can solve this problem using a gradient descent, right? So we can compute the gradient again, right, with respect to W. So the gradient is given by this term, and we can use an iterative update procedure to actually minimize the loss function and find the optimal value of W. So it would make much more sense when we represent it in the other format. So for example, let's consider the objective function as sum over I equal to 1 to m. To make it more clear, yi minus phi of xi transpose times W square plus lambda times W transpose W. So we can compute the gradient of this loss function would be the gradient of this term plus the gradient of this term plus the gradient of lambda times W transpose W. So this is simply twice of yi. I forgot the summation. So this is simply equal to sum or I equal to 1 to m twice of yi minus phi of xi transpose times w times the derivative of this term, which is negative of phi of xi plus the gradient of this, which is just so as we discussed in the previous lecture as well. Instead of doing this summation over all w, we can have an online gradient descent or a stochastic gradient descent where we update based on each sample. So the update equation would look like, in the gradient descent, w goes to w plus some learning rate. So we can just drop the 2 in the equation here since we have a learning rate. So alpha times, based on each sample, we'll go in the direction of the negative of the gradient. So this would be yi minus phi of, note the negative sign over here. So when taking the negative of the gradient, this negative will become positive. Phi of xi transpose times w times phi of xi minus lambda alpha w. So this would be the update equation in the gradient descent algorithm. In the online gradient descent, in the batch gradient descent, for every update we have to compute this. We have to sum it over all the data points, but with online gradient descent, we can do it over all the data points. So as you can see here, irrespective of the error in prediction, we always decrease the value of w, right? In each update, we are making w more close to 0. So as you can see in the closed form solution, the closed form solution is given by w star equal to lambda I plus phi transpose phi inverse times phi transpose times y, and the gradient descent rule, if we solve it using gradient descent, then we have an update rule as w new is equals to w old plus some learning rate alpha times yi minus phi of xi transpose times w old times phi of xi minus lambda times w. So here we have seen how to compute the optimal solution w for the L2 norm regularized least square problem, and now we will see how to optimize the L1 norm regularized least square. It turns out because of the L1 norm, the entire objective function becomes non-differentiable. So what we will have instead of gradient descent, we will have sub-gradient descent algorithm. The sub-gradient descent algorithm. Along with that, we'll it's been established in the machine literature that using just naive sub-gradient descent is very slow for optimizing the objective to compute the optimal parameters w. It's very slow to minimize the loss function if we use a naive sub-gradient descent. So instead, we'll study an algorithm known as, and we'll derive its entire formulation. We'll entirely derive the algorithm ISTA, ISTA, which is iterative soft thresholding algorithm. So this is going to be the next part of this lecture.